In this video, we're going to talk about 8.1 basic integration rules. This is just going to be a review of procedures for fitting an integrand to one of the basic integration rules. So we've talked about already from chapter 4 and chapter 5 before we get on to some more advanced integration techniques in chapter 8. So example 1 here will be a comparison of these three similar integrals. So let's compare the methods of integrating these three integrals. Recall first that we have the integral of 1 over u du is equal to ln of the absolute value of u plus c. That's one of our techniques that we learned in chapter 5. It's a basic integration rule. So if we try to do that with number 1, it won't work, or with letter A, because if u is equal to x squared plus 9, du is going to be 2x dx. That's going to fit with a b. So, so we know with b down here, we're going to be trying to get 2x dx in the top. So I'm going to factor out a 2. I'm left with 2x dx in the top and x squared plus 9 in the bottom. So I get 2 integral of du over u is 2 ln of the absolute value of u plus c is 2 ln of, I don't need absolute value bars because x squared plus 9 is always positive, plus c. For A, because I have an x squared and I have a dx here, I'm going to be thinking of an arctangent rule. This can be 4 integral of dx over x squared plus 3 squared. Recall here that the integral of du over u squared plus a squared is equal to 1 over a arctangent of u over a plus c. So we have our u was x, du is dx, our a is 3. So this is going to be 4 times 1 over 3 arctangent of x over 3 plus c. So that's going to be 4/3 arctangent of x over 3 plus c. For c, we have degree of the top and degree of the bottom are the same. We're going to have to use long division of polynomials. So we have x squared plus 9 into 4x squared plus 0x plus 0. It's going to be a 4x squared and 36. Subtract. Get a negative 36, so that's minus 36 over x squared plus 9. So this integral here of 4x squared over x squared plus 9 dx changes into the integral of 4 dx minus 36 integral of dx over x squared plus 9. This is 4x minus 36. We already did this part just a second ago up here. So this is going to be over 3 arctangent of x over 3 plus c. That's going to be 12. So 4x minus 12 arctangent of x over 3 plus c. Now we have 0 to 1 of x plus 3 over 4 minus x squared dx. So let's try u equals 4 minus x squared, and du is equal to negative 2x dx. Let's split the integral here. 0 to 1 x dx over root 4 minus x squared plus 3 root 4 minus x squared dx, like so. Then we're able to make this a negative 2 and a negative 1/2 here to fix that one for integral 1. It's right here. This is going to be integral 2. So let's finish up with integral 1. We have negative 1/2 of u to the negative 1/2 du. And if we stick in 0 here, we get 4. If we stick in 1 there, we get 3. And our limits are upside down, so we need to switch them and change the sign here. It's going to be 1/2 of 3 to 4 u to the negative 1/2 du. It's going to be 1/2, then u to the 1/2 divided by 1/2 is going to be times 2 from 3 to 4. That's going to be 4 to the 1/2 minus 3 to the 1/2 is 2 minus root 3. So now for part 2, we need to use an arcsine rule where we have integral of dx over square root of a squared minus u squared is equal to arc sine of u over a plus c. There's no 1 over a in this rule, so our a is equal to 2, our u is equal to x, and our du is equal to dx. So we just have a multiplier of 3 out front, and this is going to be arcsine of x over 2 evaluated from 0 to 1, like so. And that's going to be 3 arcsine of 1/2 minus 3 arcsine of 0. Arcsine of 1/2 is pi over 6. And then that's arcsine of 0 is 0. So that's plus pi over 2 minus 0 is plus pi over 2. So my overall answer here is going to be 2 minus the square root of 3 plus pi over 2. And that's going to be about 1.839 if we approximate that. Now we have a little bit of a more advanced arcsine integral here, where we see that we have a constant squared minus a function of x squared, where our function of x is equal to x cubed. This is supposed to say x squared. Not x cubed. So integral of x squared over root 16 minus x to the sixth here. We're going to have u is going to be equal to x to the third. Du is going to be 3x squared dx. A is equal to 4. So we need a 3 and a 1/3 here. So this is going to be 1/3 integral du over root a squared minus u squared. It's going to be 1/3 arc sine of u over a plus c. It's going to be 1/3 arc sine of x cubed over 4 plus c. All right. Now we have a log rule in disguise because we need to integrate using an integration factor. We're going to multiply top and bottom of the fraction by e to the negative x. And that's going to change this into e to the negative x dx over e to the negative x plus 1. Now our u is e to the negative x plus 1. Our du is going to be a negative e to the negative x. So we need a negative e to the negative x. That changes this into a negative integral of du over u is a negative ln of absolute value of u plus c is a negative ln of absolute value of e to the negative x plus 1 plus c. That equals ln, let's see, clean that up at all. Yeah, so let's go ahead and make this a negative ln of multiplied by e to the x over e to the x here is going to be 1 plus e to the x over e to the x. It's going to be a negative ln of 1 plus e to the x minus a negative is plus ln of e to the x plus c. Ln of e to the x is going to be x minus ln of 1 plus e to the x plus c. And we're done. If we had done division, we could have come to the same conclusion there. Let's see, what else could we have done? Could have added and subtracted e to the x in the numerator and split it up. There's all kinds of fun ways we could have worked that one. I like the integration factor technique here. That's the one that you're going to use a lot of times in differential equations. So example 5 here, we have integral of cotangent x times ln of sine of x dx. And this cotangent is cosine over sine. Like that. So our u is We have an ln of u that we're differentiating, so that's going to give us 1 over u times du dx. So the derivative with respect to x of ln of sine x is 1 over sine x times the derivative of the inside is cosine of x is that other piece. And then we have the integral then. It's going to be, let's do it this way. U equals ln of sine x. Du equals 1 over sine x times cosine of x times dx. So du equals cotangent x dx. So we have u du is going to turn into 1/2 of u squared plus c is 1/2 of ln of sine x squared plus c. We have the integral of tangent squared 2x dx. Remember that sine squared theta plus cosine squared theta is equal to 1. Remember that 1 plus cotangent squared theta is equal to cosecant squared theta, and 1 plus secant squared theta is equal to tangent squared theta. So we're going to need to change this tangent squared into a 1 plus secant squared theta. So that's going to be dx plus secant squared 2x dx, like so. And we need to fix this with a chain rule, 2 and 1/2. So that's going to make this x plus 1/2 of tangent of 2x plus c. Oops. No, that's right. Oh, right. I wrote this backwards. Ooh, I wrote something backwards. So tangent squared is secant squared minus 1. That's a minus 1. That's a negative x. Here we go. 1/2 tan 2x minus x plus c. This is like a problem in the textbook. It may not be exactly yours. It's in the textbook right now, but use the fact that this is integral of secant u tangent u du is going to be equal to secant u plus c, because the derivative of secant is secant tangent. So all we need to do to fix this is a 5 and a 1/5 to make the chain rule here, because u is equal to 5x, so du needs to be 5 dx. This is going to be 1/5 of secant of 5x plus C. Anything else? Yes. We have similar problem here. I'm going to use the integrating factor of e to the negative x here. So this is going to be 4 integral of e to the negative x dx over 3 e to the negative x minus 1. U is going to be 3e to the negative x, and du is going to be minus 1. Du is going to be a negative 3e to the negative x. So I want a negative 3 divided by a negative 3. I get a negative 4/3 ln of 3e to the negative x minus 1 plus c is negative 4/3 ln of 3 minus e to the x over e to the x plus c is, I mean, we can just leave it like this. This is fine. But negative 4/3 ln of 3 minus e to the x plus 4/3 ln of e to the x plus c is 4/3 x minus 4/3 ln the absolute value of 3 minus e to the x, just to get it back to that denominator, plus c. Example 9 here. Looks pretty gross, but we're going to think about if we can complete the square on the inside here. So first things first, I'm going to deal with 4x squared minus 8x plus 3. We'll want to factor that 4 out and leave x squared minus 2x plus 3/4 on the inside. And then we have half of the middle number squared is going to be 1. Add 1, subtract 1 here, and we're going to get 2 root x minus 1 squared minus 1/4. So I'm going to go ahead and look at the fact that this is a u squared minus a squared. Ooh, look at that. That's awesome. That's already my a. So I'm going to take the 1/2 out front. Here, let's go ahead and show you what I'm doing. This is going to be a u times 2 square root of u squared minus a squared. U is x minus 1. A is 1/2. Du is dx. So I have this 1/2 right here that needs to come out front. Du over u square root of u squared minus a squared. And that's going to be 1/2 arcsecant of the absolute value of u over a plus c. So that's going to be also a 1 over a out here in my formula. So 1 over 2 times a. So 2 times 1/2, that's going to be 1. So that's just going to make this arcsecant of absolute value of u over a plus c. It's going to make this arcsecant of 2 of these like that. And so that's going to be arc secant of the absolute value of 2x minus 2. It's probably the best way to write that, plus c. Now let's look at example 10 here. And this looks like something where I'm going to complete the square in the bottom, or factor the bottom, or something. This looks like an e to the x plus 1 squared in the bottom, e to the x dx. So u is e to the x plus 1, du is e to the x dx. And so I have du over u squared. Let's change my limits of integration if I can. U here, e to the negative third plus 1, and then e plus 1 up here. So this is e to the negative third plus 1, e plus 1, u to the negative second du is u to the negative first over negative 1, evaluated from e plus 1 on the top, e to the negative third plus 1 in the bottom, negative 1 over u. Like so. It's going to be a negative 1 over e plus 1 plus 1 over e to the negative third plus 1. And we can do some fancy factoring in a second. Multiply by e to the third here. For e to the third, it's e to the third over e to the third plus 1 minus 1 over e plus 1. This denominator over here factors into e plus 1 times e squared plus e plus 1. So I need to multiply top and bottom by that here to get e cubed plus 1 there as well. So that's going to be exactly e to the third minus e squared minus e minus 1 over e cubed plus 1 is exactly what my answer is, and that should be about 0.684. Yep. All right. If we have some extra examples, we'll come back and work those maybe at a later time. But for the next video, we're just going to move right on to 8.2, where we're going to start talking about integration by parts, which is a really big new integration technique in Calculus 2. So see you for the next video.